Alright, so today we'll be doing the complete topic of your Module 6 OCR A-Level Physics, Chapter number 23, Magnetic Fields. Our Earth is also part of a magnetic field, and you have already talked about two different fields as well as a part of your course, including the electric field and the gravitational field. You have already stated that electric field is a region where a charge, a point charge, whether a positive charge or a negative charge, experiences a force. We call that area as an electric field. Versus if we talk about a gravitational field, we are a part of a gravitational field as well because we, being a point mass, are experiencing a force of weight due to our gravity as well. Any magnetic field will be an area where an object is going to face magnetic force. Our Earth also has a magnetic field just like that of a bar magnet, where the magnetic north and south pole, and it is caused by electric current circulating in the molten iron of the Earth's core as well. So it's basically a field that surrounds a permanent magnet or a current carrying conductor in which magnetic objects experience a force, and you can also detect the presence of the magnetic field by using the plotting compasses, and then you can plot those magnetic field lines. And remember, the magnetic field lines always start from north and they end at which pole? South pole. Clear?
Yeah.
So the arrow on the magnetic field line is the direction which a free north pole could move, and it always points from north to south, and they are all equally spaced as well. They are all parallel as well. And remember, they are never going to cut each other. They are never going to cross or overlap each other as well. And where will the magnetic field be stronger?
Um, because this is the poles.
When, yes, closer to the poles and where the lines are closer together as well. Got it? You can see that the lines are more closer in this area versus this area. Clear? This is where the magnetic field will be stronger versus this area where the field lines have a lot of gaps between them as well. Clear?
Yeah.
Like poles always repel each other and unlike poles always attract each other. Figure 2 shows the magnetic field patterns for a bar magnet and the earth, and you may already have seen how the iron fillings can also reveal a magnetic field around a bar magnet, and that field induces magnetism in the fillings as well. But what is electromagnetism then? Electromagnetism is a different thing where any object or any material will only behave as a magnet. There will only be a magnetic field until we are providing a current. The moment you are going to switch off the current, there will be no more magnetism as well because this magnetism was only dependent on electricity. We call it an electromagnet, a magnet that only acts as a magnet when there is electricity passing through it. But if there is no electricity, it won't act as a magnet. There would be no magnetic field or any kind of magnetic force as well. You can see how between unlike poles there is attraction, how between like poles you are showing repulsion over here. For a current carrying wire, the magnetic field lines are always concentric circles. Concentric circles mean they are all equally spaced circles, they don't cross each other. Well, you can use the right hand grip rule in order to tell the direction of the convection current in a thumb as well. Got it? Let's say this is a wire. What is the direction of the current?
It's, it's uh
Upwards. The current is
quite
upwards, right? So if you
yeah.
use the right hand grip rule, your curl of fingers are going to be in which direction? Clockwise or anti-clockwise?
Uh, isn't it? Let me see.
Use your
Anti-clockwise.
right hand, point the thumb in the upward direction, and the curl of fingers is in which direction? Clockwise or anti-clockwise?
With the thumb in the upwards direction.
Yes, the thumb should be in the upward direction like this.
Then it's anti-clockwise.
Exactly. The curl of the fingers will tell you that there will be an anti-clockwise magnetic field. If I use this sign means what? Into page. Now point your thumb into the screen and tell me the curl of fingers.
It's still anti-clockwise.
No, point your thumb into the screen. This cross means into page.
I am.
Check again. Right hand.
Yeah.
Point your thumb into the screen. So
When
what
you
does the curl of your fingers tell you?
it's going left to right.
So it's clockwise, no? It's clockwise.
Isn't clockwise. Oh.
Clear or no?
Uh
Now this
yeah.
sign means out of page. Now point your thumb towards your face, out of the screen. Point your right hand thumb towards your nose. Tell me the curl of fingers.
It's clockwise.
No.
Is
Are
it
you
anti-clock?
using your right hand or no?
I'm using my right hand.
Right hand, make a thumbs up, make a thumbs up, point the
Yeah,
thumb towards your nose.
yeah,
Tell me the direction of the curl
anti-clockwise.
of it. It's anti-clockwise, got it?
Yeah,
Good. And when it's into the screen, then it is
clockwise.
clockwise. Clear or no?
Um, yeah, kinda.
Why? Try again. Now let's say there's a wire and the current is in downwards direction. Now let me know how will a magnetic field form. Make a thumbs down. Where is your
Um,
curls of finger? Clockwise.
yeah, clockwise.
Now you're getting it? Good. This is how we use the right hand grip rule. And even inside a solenoid, when a current passed, we can also determine the direction of the magnetic field as well. That how is a uniform field going to be created over here. And this cross means what? Cross means into page. Dot means out of page. Got it? The thumb will be pointing outwards. Cross means the thumb will be pointing into page, which means the current is going into the page. Clear?
Yeah,
Then we have another rule as well, known as what?
that means left hand rule.
Fleming's left hand rule. How do we use the Fleming's left hand rule? The thumb represents what?
The magnetic field, the motion, the force.
The motion, or yes, the force. What does the first finger tell you?
Uh, the magnetic field.
Exactly. And what does the third middle finger tell you? The second finger? Exactly. It will tell you the current. Got it? Now look at this. Current's direction is out of page or into page.
Uh,
You can see a dot or a cross. What does a dot mean?
the
And what
dot
does it
means out, out of page.
exactly? Dot means out of page. Cross means into
Yeah,
page. Now use your Fleming's left hand rule.
the current's going right.
The current is going out of page. How is it going right?
Oh,
Can't you see this dot? What does the dot mean? That the current
uh,
is towards your nose. Okay.
the current. So the dot is the current.
Yes. The dot
Okay.
or the cross is the current. If it's a cross, it means that the current is inside, into the screen, into the page. Got it? The dot
Yeah.
means that the current is out of the page. Now, out of the page means that point the middle finger of your Fleming's left hand rule towards your nose. Your first finger should be pointing in this direction from north to south. And tell me, where is the thumb pointing now automatically?
Up.
Upwards. Clear?
Yeah.
Good job. That is how you use the Fleming's left hand rule. The first finger gives the direction of the external magnetic field, second finger gives the direction of the conventional current, and the thumb gives the direction of motion or the force of the wire. The magnitude of the force experienced by the wire in an external magnetic field depends on number of factors. For example, the force will be maximum when the wire will be exactly perpendicular to the field. Perpendicular mean it would be exactly 90-degree with the magnetic field as well, but it will be zero. When will it be zero? When will the
Uh,
force be zero? When it is parallel to the magnetic field. Experiments also show that the magnitude of the force experienced by the wire is directly proportional to current, length, angle, and the strength of magnetic field as well. When we have a greater magnetic field strength, greater magnetic flux density, greater will be the force. B represents what? The magnetic flux density. And this is the formula that we have. F is equal to BIL sine theta. Got it?
yeah.
B represents the strength of the field, magnetic field strength, magnetic flux density, whatever you want to call that, which is analogous to the electric field strength as well. Magnetic flux density B, what is B measured in? Tesla. B is measured in Tesla. When the wire is perpendicular to the magnetic field, it will have theta 90, and that means that the force is going to be maximum because what is sine 90? Sine 90 is equal to 1. So then the formula becomes what? Just simple F is equal to BIL. No need to add the sine theta as well. And if you want to find B, you can rearrange the formula. And what does the formula become?
Equals F over IL.
F over IL. Exactly. Explain me this question.
Um,
Take 1 minute and then explain.
okay. So they use the wire is the weight of the wire is 1.8 times 10 to the negative 3. So that means the force is 1.8 times 10 to the negative 3. And then the magnetic flux density is 0.15 Teslas, while the
Mhm.
length is what?
What do we have to find in this question?
We have to find the
Okay, then tell me how they find the current.
current of wire, so they increase from 0 to y express. Wait, I'm not sure where they got the length from.
Let me check. Have they not given the length? The
No,
length is
unless
there. Think where did they get the length? A thin wire, weight is this, horizontal with the magnetic flux density this. The current in the wire is slowly increased from zero. The wire experiences a force vertically upwards. Calculate the size of the current in the wire such that the wire just starts to lift itself vertically.
so they
Yeah.
assumed it's 0.01.
Yeah, I guess they've just assumed it 0.01 because the wire was having a weight of how much? 1.8 into 10 to the minus 3 per centimeter, right?
Yeah,
And 1 centimeter is equal to,
0.01 meters.
now clear?
Yeah,
Good, and that's how they just use the formula to find the current. Figure 4 also shows some apparatus to determine the magnetic flux density B between two magnets. The magnets are placed on top pan balance and the magnetic field between them is almost uniform. A stiff copper wire is held perpendicular to the magnetic field between the poles. Perpendicular again means that the sign will be sine 90. Sine 90 is equal to 1. That means we'll have now maximum force over here, and this is how you can calculate the magnetic flux density as well. You can vary the current, you can vary the voltage as well, and this is how an arrangement of determining the B in laboratory. You basically have to tell what will be the force on this wire due to the changing magnetic field, and when there is a force, obviously the mass balance, the top band balance that is measuring the mass at value is also going to change because the force on the wire is going to be changed as well. Is it clear?
yeah.
So what are the two rules that we have talked about till now?
For the magnetic field,
Yes.
um,
Right hand rule and
oh, the right hand rule and Fleming's left hand rule.
Fleming's left hand rule. Exactly. What do they both tell us?
Uh, the direction of current
Good.
and any other
Mhm.
like force as well for left hand rule.
Good job. Good job. And yeah, okay. This is clear. This is clear as well. Let me show you the different magnetic field current flowing patterns. Yeah, wait. Let's click a project can go from magnetic fields are mapped using magnetic field lines,
which we sometimes call lines of flux. And you can see on this diagram of a bar magnet an example of magnetic field lines. These lines show the direction of the force that would act on a north pole at that point in the field. This is similar to electric field lines, showing the direction of force on a positive charge. So here we have our north pole, and it's experiencing a force away from this other north pole here. So the field line is pointing in this direction. Here we have a north pole that's being acted on with a force in this direction, following the field lines, and here the force acts in this direction towards the south pole. The magnetic field lines are continuous and must flow from north to south. And we can see that all of these field lines originate at the north pole and curve around towards the south pole. This explains why like poles repel and unlike poles attract. So the field lines are pointing from north to south. So the North Pole is going to move towards the South Pole, and therefore they're attracted. However, here we see that there are no field lines and the North Poles are pushed away from each other, so they repel. Now we're going to discuss the Earth's magnetic field. The Earth's magnetic field is actually very similar to the field produced by a bar magnet. So here's the field lines around a normal bar magnet, and here's Earth. And Earth acts like a bar magnet. The Earth's bar magnet will have to have its south pole at the north and its north pole at the south. And this might seem a bit confusing, but remember that a north-seeking north pole on a compass needs to be attracted to the south pole of the Earth's bar magnet, and vice versa. The direction of the magnetic field lines is the same as the direction of the North Pole on a compass needle. So inside the Earth we have this giant bar magnet with south here and north there, and the direction of the magnetic field lines is the same as the direction of the North Pole on a compass needle. So it's pointing this way, and the magnetic field lines are pointing that way, and here the North Pole would point this way. Now we're going to discuss magnetic field lines from a current-carrying wire. For a current-carrying wire, the magnetic field lines are concentric circles in a plane perpendicular to the length of the wire. So here we have our current-carrying wire, and the direction of the current is this way. And the magnetic field lines have to be in the plane perpendicular to the length of the wire, which means that they're in this plane here. So this is the plane of the field. And you can see that the field lines make concentric circles around the current-carrying wire. Notice that if we reverse the current, it will change the direction of the magnetic field. The relative directions are given by something known as the right-hand grip rule. So on the left, we have our current going in this way, and the magnetic field lines form concentric circles pointing in this direction. If we reverse the current, then the magnetic field lines will also reverse direction. So now they're going in the opposite direction. The relative directions of the magnetic field are given by something known as the right-hand grip rule. Imagine if we grip the wire with our right hand and extend our thumb in a thumbs-up position. So here's the wire. Here's our thumb pointing upwards parallel to the wire. So the wire and our thumb are parallel. And this is our right hand. Our thumb points in the direction of the conventional current, and the curl of our fingers points in the direction of the magnetic field. So here's the direction of our conventional current, in the same direction as the thumb, and the curl of our fingers around this way point in the direction of the magnetic field, as you can see here. And when we say conventional current, we mean the direction that positive charge would flow in a conductor. So if the positive charge is flowing this way, that means that current is flowing in the same direction.
We are pioneers for engineering.
Is it clear?
Yeah.
How do different charged particles behave in a magnetic field? Some of them take helical paths as well. Some of them are going to take circular paths as well. A charged particle moving in a magnetic field will experience a force, and this effect can be demonstrated for a beam of electrons using an electron deflection tube. The force on the beam of electrons can be predicted using Fleming's left-hand rule, and the beam of the electrons is also moving from left to right in a region of a uniform magnetic field. As the electrons enter the field, now electrons are what? Negatively charged. They experience a downward force and the electrons then change direction. But the force on each electron always remains perpendicular to its velocity, and the speed of electron remains unchanged because it's all a uniform magnetic field. And the force on the electron acts downwards over here, like you can see. Clear? Look
Yeah.
at Look at how the electron beam's direction is changing. A current carrying wire in a uniform magnetic field also experiences a force because each electron moving within the wire experiences a tiny force. To find the force acting on a charged particle of charge q moving at a speed v at right angles to a uniform magnetic field at flux density b, you can consider, let's say, a beam of charged particles, like we have talked about the electrons as well. V calculated by F is equal to BIL. Now in place of length, we know that distance is equal to speed into time, right? So in place of L, can we write V into T, speed into time? We also know that I is equal to what? Number of charged particles passing per unit time, right? So
Yeah.
can I say B in place of I can write NQOT. In place of length, I can write speed into time. That gives me what? NBQV, because this T and T cancels out. So the final formula of F we get is NBQV. And the force on each charged particles, if we cancel out the number, you can then make this formula as F is equal to BQV. And if the charged particle is electron, what can we call it? E. So in place of Q, we write what? F is equal to BeV. And what is the charge of an electron?
Uh, it's -1.
No. The actual elementary charge of an electron is?
1.6 times 10 to the -19.
Exactly. Explain me this example as well.
Um, so they're solving for acceleration. What to do is they use the magnetic flux density, which is 0.15 Teslas,
Mm-hmm.
and they use the equation F equals ma and make it equal to BQV because F also equals BQV. And they do 0.15
Mm-hmm.
times the elementary charge, which is 1.6 times 10 to the -19, times 5 times 10 to the 6 over the mass of an electron, which is 9.11 times 10 to the -31. And then that gives them the acceleration, which is 1.3 times 10 to the 17.
Claire, you know what is F is equal to ma? You have seen that before from Newton's second law as well, Claire.
Yeah.
Consider a charged particle of mass m and charge q moving at right angles to a uniform magnetic field of flux density b. The particle will describe a circular path because we just talked about that the force will always act perpendicular to the velocity, and we can say the centripetal force on the particle is also provided by the magnetic field. We talked about centripetal force in circular motion as well, and can we equate this centripetal force equal to the magnetic force, because this centripetal force right now that is causing the charged particle to move in a circular path is caused by which force? The magnetic force. So that is why we have equated magnetic force to centripetal force. Got it?
Yeah.
Good. So now we know, according to this relationship, that faster moving particles travel in bigger cycles, more massive particles move in bigger circles. Stronger the magnetic fields mean that the radius, they would move in a smaller radius. Strong magnetic field means a smaller radius or a circle will be produced. And a greater charge will also mean smaller circles. Clear?
Yeah.
Now let's say if we have to equate these two equations, take 1 minute and then you'll have to explain me this worked example, that why have they equated magnetic force with centripetal force as well, and that can only happen if the charged particle centripetal force is caused by magnetic force. And then you'll also have to tell me what are they actually calculating.
Okay.
Yes, can you explain me?
Um, so they use the formula BQV, which equals uh, mv squared r, and that's because of F equals ma,
Mm-hmm.
and I mean, they equated B cubed V to mv squared over R, and they substituted the values, then rearranged it to find B, and then that gave them 3 times 10 to the negative 3 Teslas.
Good job. Clear?
Yeah.
A velocity selector is a device that uses both electrical and magnetic fields to select the charged particles of specific velocity, and then only you can use the electron beam guns or spectrometers in order to accelerate those particles as well. It basically consists of two parallel horizontal plates that are connected to a power supply, and they produce a uniform electric field of a field strength E between the plates. A uniform magnetic field of flux density B is also applied perpendicular to the electric field. The charged particles traveling at different speeds to be sorted enter through a narrow slit Y, and the electric and magnetic field then deflect them in opposite direction. So only for the particles with a specific speed v will these deflections cancel, so they travel in the straight line. Sometimes that electric force, if that magnetic field is being created through electricity, we can say that the electric force is also equal to the magnetic force. And if you cancel out the charge on both of the sides of the equation, the final formula becomes what?
It becomes V equals EB.
V is equal to E over B. Clear?
Yeah.
Good job. That's what the mass spectrometers also do. There's basically an ion source that produces charged particles. We have a velocity selector that then accelerates those particles through a uniform magnetic field, and then we can see their display produced on a computer as well. Hall probe is a similar device that is also used to measure the magnetic flux density directly as well, that you will be doing in the upcoming chapters as well. And there's also a specific method to calculate Hall voltage. Hall voltage is equal to E multiplied by D, or you can rearrange the equation that E is equal to Hall voltage divided by D. Not exactly part of your syllabus currently. So can you tell me, how does the magnetic force equal to the centripetal force in which cases?
Like the formula.
Yes.
Um, so because of the formula of the velocity selector, which is
I mean, that's
V,
the electric force equal to magnetic force. In what cases have you seen that the magnetic force was equal to centripetal force?
isn't that
Mhm.
the
And you have
formula?
seen the path of the charged particles as well. Clear? In the electron deflection tube. Got it?
Yeah.
Let me show you again. Now listen very carefully, and then I'm going to ask you questions from this topic again as well. That how does the force on the moving charged particle is affected? Okay. Now,
Okay.
Let's think about the magnetic force acting on a charged particle. Moving charged particles can be found in many situations, including conductors, electron guns, and particle accelerators. For example, as a current goes through a solenoid, electrons are travelling through the solenoid. Electrons are also fired out of electron guns. And moving charged particles are also present in particle accelerators, like the Large Hadron Collider. In this example, a proton has been accelerated out of the particle accelerator. From our understanding of conductors, in the next few videos we're going to build a knowledge of the forces on single charged particles in a magnetic field. Let's start by imagining a positively charged proton moving freely in a direction perpendicular to a uniform magnetic field. So our uniform magnetic field is pointing into the plane of the paper, and the proton is moving perpendicular to it. As the proton is charged and moving in a magnetic field, it experiences a force. So say the proton is moving in the magnetic field created by a bar magnet. It's going to experience a certain force on it. The relative direction of the force on a charged particle in a magnetic field can be obtained using Fleming's left-hand rule. So if we take our left hand and extend the thumb and the first two fingers, the force is going to point in the same direction as the thumb. The magnetic field in the same direction as the first finger. And finally, the conventional current is going to point in the direction of the second finger. Recall that conventional current is the direction of positive charge flow, so we can also call the second finger the direction of motion of a positive charge. Since the proton is positive, the direction of the force it experiences can be read directly from Fleming's left-hand rule. So here, the first finger is representing the magnetic field into the plane of the page, and the direction of motion is in the direction of the second finger, and it's pointing from left to right. And then the thumb points in the direction of the force, which we can see as upwards. When dealing with a negative charge, we can use our right hand. So this time, if we use our right hand, the first finger is still going to point in the direction of the magnetic field, and the thumb is going to point in the same direction as the force. But this time, the second finger is going to point in the direction of motion of a negative charge. We can never use our right hand when we're dealing with current, only for motion of negative charges. A negative charge, like an electron, would have to move in the opposite direction to a proton to experience the same force. So here we have a proton, and its direction of motion is from left to right. And so if we illustrate this on our left hand, we can see that the magnetic field points into the plane of the paper, and the direction of motion of the proton is from left to right, and therefore the force acts upwards. In order for our electron, which is negatively charged, to experience the same force upwards as the proton, using our right hand and having force in the same direction as the thumb and magnetic field strength in the same direction as the first finger, we can see that the direction of motion, which is given by the second finger, is from right to left. So it's opposite to the proton. Now we're going to think about the path that a charged particle might follow in a magnetic field. The force on a charged particle due to a magnetic field is always perpendicular to the particle's direction of motion. So here's our direction of motion. And if we use our left-hand rule, we'll find out that the force is acting downwards, and it is perpendicular to the direction of motion. Recall that the work done on an object is equal to the force in the direction of motion of the object multiplied by the displacement. So the work done in joules, W, is equal to the force applied in the direction of motion, F, which is measured in newtons, times displacement, S, which is measured in meters. Note that velocity is perpendicular to the direction of the force, so there's never any displacement in the direction of force, and so the work done is zero. Since we have no force applied in the direction of the particle's velocity, no work is going to be done by the magnetic field on the particle. So our velocity is perpendicular to the force.
Hi, my name is Alexander Bondar, and I'm the VP.
Everything clear till here?
Yeah.
Kinetic energy and speed of the charge must be constant. So our kinetic energy is a constant. And recall that our formula for kinetic energy is a half times mass times the magnitude of velocity squared. And we know that mass remains constant throughout, so the kinetic energy is constant, therefore the magnitude of velocity, or the speed, must also be constant. However, the force acting on the particle will still result in a change of velocity. Although the speed is constant, its direction is going to change. So here we see the force on the particle causing the direction of motion to change. And note that the speed remains constant. The direction of velocity is constrained to the plane of the screen because it must remain perpendicular to the magnetic field and force. So here we see that although the direction of motion is changing, the velocity is always in the same plane and is always perpendicular to the force. This means that the force on the particle will always be directed inwards, so it will move in a circular path. And we can see here that the force on the particle causes it to move in a circular path, and that the velocity is always perpendicular to the force. And this is how we're able to trap charged particles in a certain region. And this is used in particle accelerators. Now we're going to discuss a particular use of the movement of charged particles in a magnetic field, which is the electron deflection tube. We can demonstrate the circular path of charged particles using an electron deflection tube. This consists of several elements. Firstly, an anode, which is supplied with a high voltage. The anode sends a beam of electrons into a vacuum tube, and we can see the electron track moving through the vacuum tube. There's also a screen and a magnetic field going into the screen. The direction that the charged particle curves within a uniform magnetic field reveals whether it is positive or negatively charged. So our first finger points into the plane of the paper, and if the current is pointing in this direction, then the force is going to point downwards. So we see from the direction of our curved track that the force is pointing downwards. And using our left-hand rule, we see that conventional current would be pointing in this direction, which remember is the flow of positively charged particles. However, we see that the direction of motion is opposite to this, because the anode is firing electrons in this direction. And this means that our beam of particles must be negative. Hey guys, I hope you enjoyed.
Is it clear?
Yeah.
Okay, I'm sending the link again, then join again, okay?
Okay.